Welcome back. In this session, we'll start with the discussion on filters. Let's start. So, what's a filter? A filter, as the name suggests, seems something which allows something to pass and rejects other things. Now, as an electrical engineer, a system, and this a filter is a system or a device. So, it's a system which allows some frequencies to pass and rejects other frequencies. So as an electrical engineer, we can define a filter is a system which allows some frequencies to pass and rejects other frequencies. Means rejects some frequencies and allows some frequencies to pass. Now, so this is the definition of a filter. So we can say it's a system which has an input and has an output, and this system is a filter. What this system will do, it will try to pass some frequency. I mean, if the input frequency is something, so this will allow some of the frequency values to pass and reject it. In other words, the output will be zero for some frequency. So the output will be zero for some frequency value. That's the meaning of filter, right? So we can say it's a system which allows some frequencies or which allows an input to pass at some frequency and rejects the other frequencies and rejects the other frequencies. Now, how do we classify this filter, and how do we say a filter is this type or that type? Based on the frequency response of the filter, frequency response of this filter, we can classify it as low pass filter. So we can classify this filter as low pass filter. Now, what do you mean by a low pass filter? A low pass filter is one which allows low frequencies pass and rejects higher frequencies. Rejects higher frequencies. Right? So how do we draw this plan? Now let me go from a system perspective. Now if this filter is a low pass filter, now what will this will pass the lower frequency. It means when the frequency value of the signal is low, we will have some output at the output. But if the frequency of the input increases, the output for that input will be zero. That's the meaning of filter, literal meaning of a filter. Now let me draw the frequency response of this. Let's draw the frequency response of this, and this is an ideal low pass filter. Now what do you mean by ideal low pass filter? That we'll learn later. So what this filter will do, this will allow frequencies from 0 to suppose omega c. Let me take this omega. This will allow these frequencies to pass and reject the higher order frequencies. Means as frequency become greater than omega c, this does not allow these frequencies to pass, and this is the magnitude response of this filter. Now let me give you the description of this from the system perspective. So if this system is a filter, so if this system is a filter that has an input x of t and the output is y of t, and this is our filter. Now in the frequency domain, I can also write it as x of s. I can write the transfer function of this as h of s, and I can write the transfer function of this as, sorry, the output as y of s. We know y of s is equal to x of s, h of s. And in this is the relationship in s domain. Now the same relationship in omega means the Fourier transform of this will be like this. So they will be connected by the same h of omega. So this is the input-output relationship in frequency domain. This is in S domain. This is in Fourier transform domain. All right. So this is how output. Now have a look at this. When the input has frequency, means when omega is less than this, what will happen? Output is directly equal to the input when omega is less or equal to omega, right? So this is the meaning of this, that it will allow the lower frequencies to pass and reject the higher frequencies, and the output will be zero when omega is greater than omega c, right? So you can check the output becomes zero. Why? Because the h omega value of the h omega becomes zero. So h omega multiplied by x of omega is zero. So you can have, this is the meaning of a filter, literal meaning of a filter. So when the input frequency is less or equal to omega c, these frequencies are passed by this system, or you can say the output is directly equal to the input like this, right? Now it may allow a different gain. For example, the gain may be 1, 2, or it may be 0.5, but it will have some value. It won't be zero. But if when the frequency becomes greater than this omega c, we say the output of the system becomes zero. So the output of this filter becomes zero. This is the literal meaning of a filter. Now, so what is this omega? This is called the cutoff frequency. This is referred as cutoff frequency. So below cutoff frequency, this low pass filter allows the frequencies to pass and it rejects the higher order frequency. Now I have given you the description in terms of system as well, right? This becomes so that you understand what do you mean by this. So if this is a low pass filter, this will allow some frequencies to pass and reject the other frequency, higher order frequencies greater than omega c. And this frequency band means from 0 to omega c is referred as pass band. This is referred as pass band because this is the band of frequency which is allowed by the system or this filter to pass, and this is referred as stop band. So stop band is above omega c. All right. So this is the stop band of this filter, and this is the pass band of this filter, and this is referred as low pass. Why it is called a low pass one more time? Because it allows the frequencies from 0 to omega c, all right, to pass and rejects the higher order frequency and rejects the frequencies greater than omega. All right. So this is the frequency response of a low pass filter, and in terms of system, I told you when the output will become equal to omega x of omega and when it will become zero. All right. Now the again based on the frequency response, we have one more type of this filter that's called the high pass filter. Now as the name suggests, high pass filter. So first let me draw the frequency response of this. Now as the name suggests, this will allow higher order frequencies to pass and does not will not allow the lower frequencies to pass. So this is a system, sorry, this is a system. So a low pass filter is a system or simply a device which will allow higher frequencies to pass and reject the lower frequencies. So this is the frequency response of a high pass filter. So beyond omega c, this will allow these frequencies to pass. So this will be the pass band of the filter, and this will be the stop band of this filter. Right? So this allows the frequencies above greater than omega c to pass and reject as the lower order frequency. So again, let me draw it from a system perspective. What do I mean it by this? System perspective. Also, if this is a system which has input x of omega directly, output is y of omega, and the transfer function of this is h of omega. Now, remember, as you can see, h of omega is equal to 0 when omega is less than omega, less or equal to omega c. And this is equal to 1. Let's assume the amplitude is 1. This is equal to 1 when omega is greater than omega c, right? So Now, how do we write the output of this system in frequency domain? We say h y of omega is h of omega times x of omega, right? So we can write the we can say the output is equal to x of omega when omega is greater or equal to omega c, and this is equal to 0 when omega is less than omega c. So what is this system doing? It's allowing the input to pass when omega is greater or equal to omega c, and it is rejecting it when it makes the output equal to 0 when omega is less than omega c. All right. So again, this is referred as the cutoff frequency. And for a high pass filter, remember the cutoff frequency is the frequency above which it allows the frequency to pass. And for a low pass filter, it is reverse. Now, again, based on this frequency characteristics of this filter, we say there is one more type of this that's referred as the band pass filter. Now, as the name suggests, this will allow a band of frequencies to pass and reject the rest of the frequencies. So let me draw the frequency characteristics of this. So we say this allows a band of frequencies to pass and rejects the other frequencies. So this will allow the frequencies from, let's suppose, omega 1, omega 2 to pass and reject the rest of the frequencies. So this is the magnitude response of this. Let's assume this is 1. So what is the stop band of this? So this is the stop band. This is again the stop band. So this has two stop bands, right? So this rejects these frequencies, this rejects these frequencies because the output will become 0 for these frequencies, right? And this is the pass band of this filter, right? Now again, you can have a look at it from the this system perspective. So the output will be equal to input between two frequencies, and for rest of the frequencies, the output will be 0. All right. Now again, omega 1 and omega 2 are referred as the cutoff frequencies of this cutoff frequencies of this filter, and sometimes we say between omega 1 and omega 2 means omega 2 minus omega 1 is referred as the bandwidth of this filter. All right, sometimes this is used, and we say the middle frequency, that's omega c, is the center frequency, right? Omega c here is the center frequency. This is the terminology. This is the terminology using band pass filter. All right. So this is a band pass filter. It will allow a band of frequencies from omega 1 to omega 2 pass, and rest of the frequencies will be rejected by this filter or by this system. Now the fourth type of the filter is the band stop filter. Band stop filter. Now, as the name suggests, this will stop a band of frequencies. So this will stop a band of frequencies. Now let me draw the frequency response of this. So this is h of omega, and let's suppose this is the magnitude. Right. So what this filter will do, this will allow frequencies from omega from 0 to omega 1 to pass, and it will again allow frequencies from omega 2 to infinity to pass, but will reject the frequencies from omega 1 to omega 2. So this is the pass band here. This is the pass band again, but this part is the stop band of this filter. Do you remember stop band means this is the band of frequency which will be, for which the output will be 0 of this system. So this is the stop band of this filter. You can again write the system output by using the description of this frequency response. All right. So this is the stop band filter. Now one important this implication of this band stop filter is, or one important type of this band stop filter is, that's referred as notch filter, and this is very popular in communication. Now what's a notch filter? It's a filter which will reject a single frequency and allow rest of the frequencies to pass. Now let me draw the frequency curve of this. So it's It's a filter which will reject only FC. Let me use C instead of FC. So this is a filter which will reject only this omega C, and omega C this time is a single frequency, and this is often used in communication to reject the power line frequency. So power line frequency is 50 hertz. We know that, right? So what this filter will do, this will try, if we design the filter, we'll try to make the system response, means the make the output of the system for 50 hertz equal to 0, and this is referred as the notch filter. This is referred as notch filter. I hope you have got the idea of this. What's a low pass, what's a high pass, what's a band pass, and what's a band stop filter. All right. And one special type of a band stop filter is a notch filter. This will reject only this frequency, rest of the frequencies will pass as it is, right? You can see the system response or the transfer function of the system is 0 when omega is equal to omega c. So rest of the frequency, the gain is, and you can say, is 1, means easily possible. All right. I hope you have got the idea. Now in the next session, now we'll see the practical filters. Now what do you mean with practical filters? Are these filters not practical? These filters are ideal filters. These filters are actually referred as ideal filters. These are referred as ideal. Why ideal? Because if you look at the transition, means the cutoff frequency of this filter, it has a sharp cutoff at omega equal to omega c. Means the output becomes, what do I mean by sharp cutoff? For example, if I say a low pass filter, now you can see the output become equal to 0 exactly at omega equal to omega c, and this is almost impossible to do this in practice. Now practically this is very hard to do this, right? So we cannot have a transition, means to make the output to go from 1 to 0 directly at one frequency, right? Instead, practically what we can have, we can make a filter to roll off with something like this, means to go to 0 as steadily, right? Not like this, means it does not have a sharp cutoff, right? That we shall see in the next session. That we will see in the next session, and the different type of filters based on that.